Well, thank you for the introduction. Today I wanted to talk to you about something I've been thinking of for the last couple of years, mostly also in my PhD thesis, which is the question of when two programs are equivalent, and basically in the setting of algebraic effects. And mainly then the question is, how do you formulate the notion of behavior of effects? And kind of in general, you can kind of see I kind of abstract this idea of program equivalence by looking at it in two different ways, like notion of proving or showing that two programs are the same, and showing that using some kind of proof that two programs are different. And so in the level of program equivalence, of course, you've kind of encountered this, and it's mentioned before that in the level of program equivalence, if you have two terms of the same type, then two programs could be proven to be the same if they simulate each other. And this gives rise to the notion of applicative similarity or bisimilarity. And then on the other hand, how could you detect that two programs are not equivalent? That would be by actually finding some observable difference between the two programs. And I've been looking at these ideas of simulation and observable differences in quite a mathematically abstract way. And basically, once we have a program with algebraic effects, these notions, we have to establish these notions. We have to actually ask ourselves what actually happens at base type, right? Because you think sometimes about program equivalence, you might think of contextual equivalence, where you detect a difference by choosing a certain context and then checking at the base type whether they're different. Or on the other hand, you might use equations at base type to say that two algebraic effects are the same. And then the main question I had, at least, is when I formulated the notion of program equivalence using specifying such distinctions, behavioral properties that could distinguish programs, I kind of used Eilenberg-Moore algebra as a foundation for checking how much a program satisfies a certain property. And in order for these two program equivalents to kind of line up, we must make sure that this notion of property checking coincides with the traditional equational axioms that you would choose for algebraic effects. And so in most examples this happened. However, the general question would then be, can we actually derive from the equations this notion of behavioral property, this notion of testing differences? So let's kind of zoom into the setting. So in order to establish these notions of equivalences, we need to start by looking at a base type, in a sense, and that's kind of the focus of this talk, and then I'll kind of mention how you can get to a program equivalence from these fundamental observations of base type. And so we're not going to look at a specific functional programming language. What we're going to look at is we're going to abstract away any of the pure computation reduction steps and going to zoom into the algebraic effect operations. And so algebraic effect operations, as many of you know, give you a way of implementing effects by saying you have a bunch of continuations, and then depending on the effect in question, a continuation is chosen. So for instance, for probabilistic choice, you might flip a coin and get a random bit, and then you have two possible continuations that you go into. The second running example we're looking at would be when we have a global store where we store a natural number, and we can look up this natural number and have countably many continuations, or we can update this global store. And this has one continuation. The last running example would be that we add a cost counter. So this could kind of signify computation steps or maybe some paywall, that when we encounter this, we assume that some cost needs to be spent before the computation can continue. And then at the fundamental level, in order to observe properties or specify properties of programs, we add these property satisfaction tokens, which have no continuation. And it's basically a failure state that can, for instance, signify divergence. And we have a success state that can signify final termination, for instance. Like if we're checking in, for instance, contextual equivalence, termination at a unit type. But more generally, we could say that if we have maybe a program of functional type, tau to tau, then we might check in what degree, what sense is the identity function. And then so we can see if it returns the identity function, then that would be a success state and otherwise a failure state. Now, in general, if we just kind of syntactically combine all these operations, we just get possibly infinite effect trees, which you could co-inductively define, which kind of look like this, and these form a monad. So here you have a probabilistic OR with two continuations, updates, lookups, and ticks, where at the foundational level we might have these success tokens and these failure tokens. But then in general, we can see this as a monad where we might apply this to a set or a pre-order of possible results that the computation can give. And then as a monad, it can be seen as a monad in the category of pre-orders because we want to check degrees of truth or like satisfaction of properties. So foundationally, we want to then associate to this monad a syntactic order, which can be given by this, where we just say that failure state is worse than anything else, and success state is better than anything else, plus lifting the underlying order. And then to specify the behavior of algebraic effects, on the one hand, as I said, we might assume some equational actions, from which then we could prove equality between more complicated terms. And so in general, when we can consider a set of variables, which we can see as x, y, z continued, like that, it will be a discrete set, and we can see these as possible continuations of a program, right? So at this point, the program terminates after some effects, and then you could potentially continue with anything you could potentially substitute for this variable. And so we see a possibly infinite tree as an algebraic expression. Then we would traditionally assume some axiomatic effect-specific equations, or even in the equations when we just say that the statement is better than the other. For instance, for probability, we might have idempotency, which says that if we have twice the same continuation, that's the same as just immediately continuing with x. Or have symmetry, or even if we have an infinitary tree, but there's still 100% chance that we get to an x, then it must still be x. And so you can see here we kind of axiomatize in a way the fact that two statements are equal if the probability to get to any of the variables is the same on either side. Similarly, for a global store, we could assume some axiomatic equations, where, for instance, if we update twice, then only the second update matters because the first update is overwritten. We update and then look up what from the global store, then we just look up whatever we just updated, and similar actions here. If we look up and everything is the same, then we didn't even have to bother to look it up. And so given these actions, we can then kind of enrich, induce an algebraic relation, which you can kind of see as anything we can show to be equal given these actions. That would be the smallest relation that has the following four properties, like reflexivity, obviously, and transitivity. We have compositionality, which means that if we substitute two similar terms on either side of an equation, then we still have an equation. We wanted to preserve the syntactic order, so still we have that failure state is worse than anything else, and success state is better than anything else, and admissibility, which deals with the infinitary tree. So if we have a tower of related terms, then their limits are also related. And this uses the fact, this is with respect to the syntactic order. This uses the fact that this syntactic order that we actually get is omega continuous. And so using this, we can, for instance, make this like a simple derivation for global store. We can prove that if we update I and then get to a success state, then with compositionality and reflexivity, we can say that this is better or equal than this statement here, but then we know if we update to j afterwards, then it's the same as update j. So we can actually prove that updating just before success state doesn't really matter, in the sense that once we reach a success state, we don't care about what the final state is, basically. This is what it implements. You might question why this would be a good result, but we'll see what kind of structure arises from this. And the same holds when we get a failure state. So failure is the same as update by failure. So on the other hand, so that's how you could go about proving at least equality between algebraic effect terms at the base level, right? So could, for instance, imagine, so let me go back, these x and y's to just be natural numbers that the program of natural numbers type returns. Similarly, what happens similarly, on the other hand, we want to specify how we can detect differences between programs. And in order to do that, we use, or at least I used, an algebra, where an algebra of a monad algebra or Eilenberg-Moore algebra of this of a particular monad in general, but the tree monad specifically is given by this map here that uses some carrier set and takes TO and goes to O, where we work in the category of preorders, where we see kind of O as a generalized notion of basically prop, but a quantitative, in this case, is a quantitative truth space. For instance, in the case of probabilistic randomized programs, this truth space will be given by the interval from 0 to 1, giving probabilities that statements are true, and which we will see later on as well. And fundamentally, what is the use of using algebra? Well, what we have is, if we have any predicate, any test on return values, which is given by some set x, then we can always lift it using this algebra to a predicate on computations that return this x, values of this x. And this can then be given as a foundation, not only of giving an algebraic relation, but also of program equivalences of programs of higher type. But at the very least, at the base level, it induces an algebraic relation on basically trees of variables given by this, and this basically spells out what would be a distinction test of this kind, where say E1 is related to E2 via alpha if for any substitution of true values seen as a predicate on variables, this, how much we get here, is smaller or equal than how much we get here. We'll look at some examples in a moment, but first of all, I'll immediately show you why this is an algebra is natural and actually can be derived directly from equations. So remember that we kind of started with a set of axioms, and that then induced an algebraic relation that is nice and compositional and reflexive and admissible and all these properties. And then what we're now interested in, and again, I'm just going to use this as an example, but remember, for instance, for contextual equivalence, you would just check for you could, for instance, only check for context of unit type, where at unit type you could say, okay, well, you can either check if it terminates or if it diverges. And so to this end, this is kind of motivation of looking at this algebraic relation when only looking at the subrelation of fundamental continuation-free computations. So this is the monad applied to the empty set. So these can only end at the failure state and the success state. And then we can say that, well, the degree of success and the degree of failure in this kind of effectfully enhanced version, because here we have also effects along the way, we say that two trees are equally successful if they're the same via the relation. So we quotient it under B in a sense where we kind of make this B symmetric, but then this quotient still has an order. Obviously, this has an injection that goes into the quotient. And then if the original relation was compositional, then we can actually extract an algebra just using the multiplication map on effect trees. And then the nice thing is then if the original relation was reflexive, transitive, and compositional, then this algebra is not only well-defined, so this lifting works, but is also an Eilenberg-Moore So let's see how much time I still have left. So let's look at two examples. So first, more of a familiar example, and I think in other works, similar observations have been made when looking, for instance, at the monad of subdistributions applied just to the unit element. In this case, we look at fundamental computation, so T applied to empty set. And if we assume the actions for probability, then we basically get binary choice tree, which can either go to a failure state or success state. And then the axiomatization, you can actually show that two things are related if the probability of getting to a success state of the left statement is smaller or equal than the probability that you get to a success state in the right statement. And so using this, basically what you get then is that the quotient that you define using these actions is you basically get the real number interval back, the example that I gave before, where basically the fundamental question would be when you're talking about program equivalence and distinction tests for checking that two programs are different would be like the fundamental observational question of what is the probability that the program does the following, like acts like an identity function or returns an even number. And then being able to observe a difference on this level could then use as foundation to actually show whether two programs of higher order type might potentially be different. The derived algebra or the constructed algebra using this form will be the expectation algebra, which checks if you have a bunch of effects and then certain probabilities, then it will give you the expected result, which locally has this definition here. So this might be a bit more traditional example. The more interesting example might be the global store. So again, I've given you the action of global store and see what we can do with it and what kind of algebra we get from this. Well, as we have seen, if we update and then get to a success or failure state, we can get rid of the update. But moreover, actually using all the actions together, we can prove that any statement, basically any fundamental equation can be reduced to just a lookup and then a bunch of successes or failures, basically, just using the actions. And so we know that two statements are the same if they reduce to the same lookup thing. And so we see that on these fundamental computations, these are identified using what you could see subsets of natural numbers in this case, but natural numbers are basically the states, possible states. So in general, you could say that we retrieve the assertions on states, basically, the state predicates as the carrier set. And the constructed algebra is then the weakest precondition function that checks which initial states, gives as a result which initial states, if we run the program here, we run the program and then get the final state satisfies the final assertion. So you get the weakest precondition with these things. And this implements the fundamental observational question of for which starting states does the program satisfy a certain property, like use an even number or act like the identity function. So this gives motivation of these very natural algebras that you get for using distinction sets. Kind of a quick note. So in general, when we start with an algebra, like with a basic relation, then derives this algebraic relation, we know that the algebra that we get does not distinguish between any terms that were identified by the original relation. And moreover, if the original relation is base valued, which means that if for any substitution, any possible continuation of the program they're identified, then they're identified by duration, then we actually have that these two coincide. So it's kind of the notion of equation and the notion of algebra generating distinctions kind of completely coincide with each other. And this assumption here is actually a very reasonable assumption. Basically, in any language where you would test program equivalence by reducing things to unit type, termination of unit type, this would be relevant. And in all the examples and combination of effects that I've encountered, at least, this is a property that holds. So I don't know how much time I still have left, but let me kind of quickly hint towards how these can be used for to actually formulate program equivalences. This is actually work done in a previous paper by me in MFPS 2019 about quantitative logics for program equivalence. So in this example, you would use the algebra as a foundation of basically formulating distinction tests, quantitative, which given are by behavioral quantitative predicates, where particular for each possible type we specify some tests that could differentiate them, and then that formulates a nice notion of program equivalence, in the sense that if the carrier set of the algebra that we are using to formulate this logic is a complete lattice, and this algebra is actually omega continuous, then we can formulate this nice logic that for each of the examples gives us a congruent notion of program equivalence. And so each of these formulas, this is a kind of example of this implementation for Calvert push value language. Each of these formulas gives you a property that could distinguish terms. On the other hand, we could also formulate applicative by similarity and similarity. In this sense, we don't want to use the algebra to lift properties, but we wanted to use it to lift relations in order to define a notion of applicative simulation, where the applicative simulation has the advantage of being able to prove the equivalence between two terms. And that can be done by specifying a relator in the sense of Ugo Dalago, Francesco Gavazza, and Paul Levy. In particular in this way here, where if we say that two predicates, we lift a relation on x and y to a relation on tx and ty. So this is kind of the other sense. And then we get, again, the same thing. So if we have the notion of equation coinciding with the notion of algebra, then, well, at least for each algebra, this notion of program equivalence, this applicative similarity, kind of gives you coincides with the notion of program equivalence that you get from the quantitative logic. Now I want to that's kind of a quick summary of that. I just want to look at two more examples. Like the tick example, if we associate the cost, we might assume that associating cost tick x is worse than x. And if we assume that, we can actually derive that following things. And using just this equation, we get the notion of algebra that returns as a carrier certain costs until we get termination, or divergence, which is the carrier set, and as algebra you get the tally operation. And this implements a fundamental question: for which price does the program produce an even number? Assuming that if it doesn't produce an even number, the price is infinite, basically. Similarly, we can look at effect combination. So if you take the Lavier theory, the tensor of Lavier theories on the equational actions here, then what we actually, and just use this as equational thing, if we then construct the algebra, then we get the weakest probabilistic precondition, where the carrier is given by, for each starting state, what is the probability that the program satisfies the property. All right, so here's a quick kind of an overview of what I actually presented. So on the one hand, we have equational actions or maybe even inequations, where you kind of order them in a sense, which produces an algebraic relation. On the other hand, we might have an Eilenberg-Moore algebra or monad algebra that produces algebraic relation. And I've shown that you can go from this algebraic relation that has these nice properties. We can actually construct this EM algebra, which if this relation is a base value, then this is a one-to-one correspondence. Moreover, we know from previous work that this EM algebra, if the underlying set is complete lattice and is omega continuous, they both formulate a notion of applicative simulation and a notion of quantitative formula, which then both imply the same notion of behavioral equivalence. So in a way, indirectly, we have a way of going from equations to both these notions of both these approaches of program equivalence. And that's where I want to leave it off. Thank you all for listening. Are there any questions?
Okay, thanks, Niels. Questions either on Zulip here?
I don't see any question in Zulip.
Okay, so maybe I have a question. So these monads are defined in the category of pre-orders.
Yes. Yeah. Yeah.
And then you can write an inequational theory for this thing, and you do kind of Lovia-like presentation of inequational theories, or how does it work?
So in the particular way that I formulated this is that we just start with some axioms, like I gave in the one slide, where we just say, well, we know that these two terms are the same, and we know that these two terms are the same, and then you choose enough axioms so you know that you've kind of captured everything, and then using that nugget, or this base of axioms, we generate the basic relation by closing this subset of pairs of expressions under particular properties, which you could kind of see as proof techniques, right? So that you add compositionality, just the fact that you can substitute related terms into variables, and also admissibility, where you can kind of approach two terms. But so I did mention Lavier theory because that is kind of the setting that people look at more generally, basically. In this particular talk and in the paper, I wanted to represent it a bit more concretely by actually just having particular elements as pairs of trees of variables, basically, that represent equality, and then derive things from there.
Okay, thanks. Any other question?
Okay, I'll ask a question online. Have you considered adding effect handlers into your framework?
Yes, so in a way that could be possible, because you could kind of see these algebras that I talked about, at least in certain cases, to be effect handlers in a sense, right? Because in global store, what you do is you keep track of which state you have, and then you go through the computation, and then you check what it is in the end. In some cases, for instance, for probability, there's not really a particular way to handle it, but still, I think there would be a way to implement these algebras in certain cases as effect handlers. Yes, that could be one way to look at to see them as. Yeah.